Hi there, folks. Today we're looking at geometric probability. And if you recall, probability is just how likely it is that an event is going to occur. We calculate theoretical probability by doing the number of favorable outcomes over the total number of possible outcomes, which is essentially just us saying, the probability of a certain event is just how many ways can we get that thing to happen over the total number of possibilities. That's what probability is. That's how it's calculated. For our purposes, we're going to calculate that based on geometric shapes and figures and those kind of things, okay? So geometric probability is a probability ratio that involves geometric measurements such as length or area, all right? So I might have like a length of something and say, what's the probability that I would land on this segment between this value and this value? And so the probability is landing on that section, which is the length of that section, over the total length of the segment, okay? In terms of area, we might say, hey, what's the probability of being in this section of the figure? Well, it's the probability would then be the area of that section over the area of the whole thing. So we're applying probability the same way that we've always done probability. We're applying it to geometric figures, okay? For example, have a look at something like this guy. Here I have a number line, and it says that point J is on SV. So point J is on SV. Segment SV is chosen at random. So we're choosing some point J at random on SV. What is the probability that point J is also on UV? And so when you kind of look at this thing, so we're choosing a point at random on SV, and we want to know if it's also on UV. And so here's the situation. I'm choosing any point somewhere along here, okay, on SV. And we want to know what's the probability that it's on this section from U to V. And so again, when we're thinking about this, the number of ways I can get what I want is basically if I land anywhere on the segment between U and V, which mathematically is represented by a value of 4 units. Okay, so there are 4 units of numbers that give me what I want here, which is being on section UV, over the total number of possibilities. Well, the total number of possibilities landing anywhere from -4 to 14. So anywhere along those 18 units. And so when you look at this, we just take the length of UV over the measurement of SV in terms of finding our probability. I can get what I want by landing on a section that is 4 units long, but the reality is that I'm landing anywhere on a section that's 8 units long, so 18 units long, and so the probability of landing on the section I want is 4 out of those 18 units, so it's 2 out of 9. Okay, so again, we're just applying probability to a geometric situation. The geometric situation being, hey, getting what I want means I can land on a length that's 4 units long, but the reality is I'm landing on a length that's 18 units long. So probability of getting what I want, 4 out of 18. Okay, so 2 over 9. It says point K is on TV, is chosen at random. So point K on TV is chosen at random. So TV, let's scroll back up here a little bit, sorry. And so TV is from here to here. So I'm choosing at random, I'm going to land somewhere on there, okay? And I want to know what the probability of K being on UT, well, UT would be from here to here. And so again, if I think about getting what I want is landing anywhere from T to U. So getting what I want, there's a length of 8 units that give me what I want. But the reality is that I have a total of 12 units that I could be landing on. Okay? So the probability for this is 8 over 12. Okay? There's a length of 8 units that I could land on to be on UT and to get what I want. But there's a length of 12 units for my total possibilities. And of course, this reduces to a 2 over 3. Okay? If I look at this next one, it says a point on the circle is chosen at random. What is the probability that it is on arc BC? And so once again, if I kind of look at it this way, I can say that, well, the central angle for BC, because I have the 152 here, this has to be a 28 degrees. And so the angle, the arc measurement in terms of degrees is also 28 degrees. And so if you think about this, we don't need any of the other information here because I'm talking about this in terms of degrees, and that's proportional to what I would get if I found the actual circumference here. I just have to find the probability in terms of degrees. So if I think about landing on BC, getting what I want, means I have a section that's 28 degrees in order to land on and get what I want out of a total of 360 possible degrees. And that's it. Like, that's my probability here. I just need to reduce this fraction. Each of these is divisible by 4 for sure. So that divides and gives me a 7. This one divides and gives me a 90. I can drop the degree symbols because they kind of cancel out. And so the probability is just 7 over 90. One of the mistakes that students make here is they think, well, I have to find the actual length of each of those things. And you don't. If I were to find the length of that arc, I would do 28 over 360 times the total circumference, which is 10 pi. That would give me the length of the arc itself, the length of BC, which, of course, if I reduce this, that's going to be a 7 over 9 pi. But then I would put that over, in terms of the probability, that's the length that gives me what I want, over the total, which is 10 pi. And what happens is these cancel, and 7/9 divided by 10 is 7 over 90. I get the same thing. And of course I would get the same thing because remember, these are proportional, okay? So when I'm doing the probability of something like this, I don't need the actual arc length. I just need any measurement of the arc because those are proportional. The degree measurements are proportional to the arc length measurements. So either one is going to give me the same values for my probability when I do this fraction, okay? If I look at this one, it says a point inside the square is chosen at random. So any point inside the square is chosen at random. What is the probability that lies in the shaded region? And so once again, what I have to do here, now we're kind of branching out and talking about area. I have to find the area of that shaded region because that area represents me getting what I want. But then I would also have to look at the area of the entire square because that represents the total possibilities. And so I look at the what I want and the total possibilities in terms of area. So let's find the area of that shaded region. To find that, I'm actually going to find the area of the square anyway. So I'm going to find the area of the square is just base times height. So area of the square. So base times height. So that's a 36 square centimeters. And then the area of the circle that's in there, let me do that down here. The area of a circle is going to be pi r squared. And for this one, remember the circle, if this is inscribed here, the radius is going to be halfway across here. So the radius is 3 centimeters this time. Okay, so that's going to be 9 pi. I guess I can just write it as 9 pi. And I'm just going to leave it as 9 pi for right now. And that's, again, square centimeters. All right, pi r squared. And so now to find the area of the shaded region, so the area of the green, I just have to take the square minus that circle, 9 pi. Okay? And once again, I'm just going to leave it like that for a moment because why plug it into my calculator just yet? Let's plug it all in one shot here. And so for this one, if I want the probability, well, that's the area of the shaded region over the area of the whole thing, which once again was the square, which is 36. And now from here, I could simplify this. I could reduce it. That's the exact area. Granted, I would have to reduce it to this. They're all divisible by 9, so that's a 4 minus pi over 4. Now, that's not a great way to represent the probability. We're used to using fractions to represent the probability, but in this one, a fraction doesn't make a whole lot of sense. So this one's better to do as a decimal, okay? So let's do 4 minus pi, and then divide that by 4. So it's a 0.215. That is an okay representation of the probability. And one of the ways that we might want to express is maybe do a percentage. So 21.5%. okay? And so remember, probability can be expressed in multiple ways. Fractions are the ones that we're used to from algebra, but you can also express probability as a decimal. You can also express probability as a percent. And when we're talking about these area problems, the decimals and percents just make a lot more sense, okay? Even in the arc length one, the previous example we have, because of that fraction being such an extreme fraction over 90, all right, it kind of loses a little bit of context, but as a percentage, it makes a lot more sense to us, okay? So we're going to typically express these as decimals and percents, especially for the area problems. If I look at this one, it says a point inside the square is chosen at random. What is the probability that it lies in the shaded region? So once again, I've got a square here, and to find that shaded region, I can just do the square minus that triangle that's in here, because this triangle is really easy to find the height of. The thing about the shaded region, if I were to look at these two triangles separately, I don't know what this value is here or this value is here. So it's hard for me to calculate the area of each of those triangles individually, because I might have a height of 5, but I don't have the base value, okay? So I can't tell where that is being split. So the only triangle I can find the area of is actually the one that's not shaded in. And so when you look at this, this has a base of 5 and a height of 5 as well, okay? Based on the square that's around it, okay? So let's find the area of the square. I guess I could do it this way. Ready? Area of the square is just base times height, so that's going to be 25 square inches. The area of the triangle is going to be 1/2 the base times the height. So 1/2 base times height, which is, once again, 25. So we can just say 12.5. And yeah, I wrote it as a decimal because it's exact. So now the area of the shaded region would be 25 the square minus that triangle, the 12.5. So the area of the shaded region is also 12.5. So now the probability is the area of the shaded region over the total possibilities, which is the 25. And so this gives me a 0.5 or 1/2 or 50%, okay? And this one actually would be good to express in any one of these formats, okay? 1/2, 0.5, 50%, any one of those would be great, okay? And again, I don't need the units anymore, because if I wrote the units here it is, square inches, the units are always going to end up canceling, or should if we're doing these properly, okay? If we take a look at the next one, it says an archery target has 5 scoring zones formed by concentric circles. Remember, concentric circles are circles that are inside of one another. They share the same center. The target's diameter is 122. The radius of the bullseye is 12.2. The width of the other zones is also 12.2. So an arrow hits the target at random. What is the probability that it hits the red zone? Okay, so once again, we have to look at these circles. We have to find the area of the thing we want. So we need to find the area of that red, of those red sections. So we're going to start by kind of looking at the entire circle. And when we look at the entire circle, it says that the diameter of the entire circle, so the whole way across here, is 122. If I want to find the area of that circle, I only need to go halfway across. Okay, so if the whole way across is 122, halfway across is going to be a 61 centimeters. So that's the radius of the overall circle. So the radius of the overall circle, 61 centimeters. I'm going to write that off to the side in case it's a little hard to see on top of the drawing there. And so from there, what I need to do is I need to find the radius of the all the way out to the red circle. And so when I kind of look at this, I'm going to erase what I have in here so far. And so when I kind of look at this, I want to find the radius from here, from the center, all the way out to the end of the red. And it was not a good choice of colors here. Yeah, let's use green. So I want to find the radius of this circle, okay? So almost like the red and the yellow together, okay? Because in order to find the area of just the red circle, I'm going to need the area of that whole circle minus the one in the middle, minus the yellow circle, okay? So looking at that radius, and what it tells me here, it says the radius of the bullseye. So right here is 12.2 for the radius of the bullseye. And then each of these sections is also 12.2 2. So the next colored zone, the red zone, is also 12.2. So we can kind of see the radius of that entire circle there. The radius of that entire circle is going to be 24.4 centimeters. Okay. So now from here, I'm going to find the area of the all the way out to the red circle. So once again, let me re-highlight it in green here. So I'm going to find the area of this whole circle. And so to find the area of that whole circle, let's see, it's pi r squared. So this is like red and yellow together. And once again, the radius of that is the 24.4. And you can use your calculator to kind of work that out. Once again, I'm going to leave it in terms of pi as well. So that's going to be a 595.36 pi. I also need now to subtract the yellow circle from that in order to get just the red area. So let's find the area of the yellow circle. So pi r squared. And again, that's just work for my calculator to do. Okay, and so now to find the area of just the red section, so area of red all by itself, I just have to subtract those two things. So the 595.36 pi minus the 148.84 pi, because again, that's just the area of that whole circle, circle outlined in red, minus the yellow piece will just leave me with the red section. And again, I can use my calculator for this. And when I do that, it looks like I get a 446.52 pi. So once again, still in terms of pi. And so that's the area of the red. If I want the probability, it's area of the red piece over the area of the whole thing. So let's do the total area. So the area of the target now, once again, is pi r squared. And the radius of the entire target is 61. And again, I'm going to leave that in terms of pi for a moment. 37, sorry, that's in 7, got a little close there. 3721. And again, that's in terms of pi. So now I have the area of the red piece. I have the area of the whole thing. Now let's find the probability. That's the area of the red piece over the area of the entire thing. And this is why we leave it in terms of pi. Right away, the pi's are going to cancel. So now all I have is the 446.52 over the 3721. Okay, and if I do that as a fraction, that's going to give me a 3 over 25. Just doing a little bit of calculator work. So we could write this probability as 3 over 25, or we could write it as a decimal 0.12, or we could write that as a percent, 12%. So that red section represents 12% of the whole target. So the probability is 3 out of 25. It's 12%. There's a 12% chance at hitting the red piece of the target if I hit the target at random. Okay?